Okay, so in the last class we were talking about the dry docking, where we take a ship to the dry dock, which will lower the water level, and consequently finally the ship will keep going down till it finally touches the bottom, and then there is a reaction force which supports the ship, and consequently the buoyancy force gets replaced by the reaction force completely, and then they put these keel blocks, they hold the things onto the ship is held firmly, and then it's okay, then the water, you don't need the water to hold the ship. So now we were doing some derivations which we didn't complete yesterday in the last class. So let's do the same thing. One part we did, the second part we need to do, that is consider this. So we are having a ship that is being dry docked. So from here we are having the reaction force from the ground, P is the reaction force. Then let us assume that this is the center line of the ship. Therefore, at this point you have G, the center of gravity of the ship. At that point the weight of the ship will act down, W. Now there is a buoyancy force acting on the ship. We know that the buoyancy force will be given by W minus P. W minus P. Now this problem, the question, what in this, there are two derivations right now which we did, one we completed last class, one which we didn't do. Now the two derivations, what is the purpose? The purpose is to find how much the GM changes. Okay, that means the metacentric height, how much the metacentric height changes as a result of this dry docking. So that is the purpose of this two exercises. Now there are two ways in which you can see a change in GM. For instance, you can look at it in two ways. One, M can decrease. Okay, then K is fixed. Let's fix G. K is fixed. Now there is a G, there is an M initially, and that is when there is no P, that is when the reaction force from the ground has not come. There is a keel which is fixed always, and there is a G and there is an M. Now the ways in which we can change GM is, for instance, suppose the M moves, okay, then the GM can change. K is fixed, but M is moving, so the GM can change. G is also fixed, I mean K is fixed, G is fixed, M is moving, therefore the GM is changing. Now another possibility is K is fixed, M is fixed, G is moving. Okay, these are two ways in which your GM can change. Now the two exercises are two ways in which you can look at the change in GM. I will explain what I mean by that. For instance, let us take the first one. Now look at this figure, that is, we have the reaction force P and we have the W minus P, the buoyancy force. Let us say this is B, which is the center of buoyancy. Here W minus P is acting, here P is acting, and G. Now there are two ways actually in which you can view this P. For instance, P, number one way is that P can be viewed as an additional buoyancy force. It is not a buoyancy force, mind you, it is a reaction force, but you can look up, it is a force upwards anyway. So you can look upon it as an additional buoyancy force, because the real buoyancy force actually becomes smaller when you compare it with P. Therefore this P can be compared as an additional buoyancy force acting at a different point. It is not acting at B, but it is acting at some other point, but it is like a buoyancy force. That is number one way in which you can view P. Number two way is, see, you have the weight of the ship acting at G. You can assume, that is the displacement of the ship acting at G. You can assume that P is like a negative displacement. That is the second way to view it. See, P is upwards, it is a force upwards. You can view it as, it is a reaction force anyway, it is not buoyancy, it is not displacement, it is not either of these, but this is a hydrostatics and stability problem. So, we are interested in buoyancy and displacement. So, two ways in which we can view P is, one, you view it as a buoyancy force acting at a different point, not at the center of buoyancy. Another view is it is a negative displacement, okay, it is upwards, it is a negative displacement acting at some other point. So, these are two ways in which you can view the same thing. So, what happens as a result? First case, you have the ship first without P and then with P. What happens is that when this P comes, there are two buoyancy forces now. There is a W minus P acting at the center of buoyancy and there is a P acting somewhere, and a resultant of these two, it can be assumed to be acting at the centroid of these two, and this is what we did in the last class. I will just explain quickly what I did in the last class also. So, this will give you the W acting somewhere in between the W minus P and P, means there are two buoyancy forces, one here, and as this figure shows, there are two buoyancy forces, W minus P here and P here, and so you can assume that there is the total force is obviously W minus P plus P W acting somewhere in between at the centroid of these two forces. Imagine there is a third force W, but that we are not considering right now. We are just saying there are two buoyancy forces, and at the centroid of the two buoyancy forces, the net buoyancy force will act. The total buoyancy force will act at the centroid of the two buoyancy forces. So, at this point somewhere in between, we know where it is, because we know W minus P and we know W. So, we know W minus P and we know P, therefore, we know where this W will act, because there are two forces acting, its centroid you can find. When that is what we did, we put x and y and we got the equation. Now, this is the first part, this is the first way of solving. Now, what happens as a result? What happens is that when you have this W minus P and an additional buoyancy force, your M, see your initial M is here. Now, because initially your M is here, your M actually can be assumed to be at M1 now. When you assume that P is a buoyancy force, what will happen is that the result is that you will see that your M has come down. Your mathematics will show that your M has come down. Okay. Now, what has happened? G has not changed, G is still the same. So, your GM has decreased. This is the first part, and we got an expression for this change in M. I will not do that again. M0, M1, it became like this. Okay, it came like this. This is M0, M1, this is the distance through which the metacenter shifts. Therefore, if we have our initial Km0 and once you have the initial Km0, which is, how do you get that? It is always got from the hydrostatic data. Hydrostatic data will always give you Km. So, Km0 means without any P, that is actually once you consider the ship, there will be some Km, and note that a metacenter is always defined for a particular draft, okay, because if the draft keeps changing, your M will keep changing. Basically, the metacenter is defined for heeling. Okay. So, you have ship like this initially upright and it heels. You know that when you put that concepts we are clear now. At that point of B, where the center of buoyancy is, you draw a vertical where it hits the initial vertical, that is called as the metacenter. That metacenter depends upon that draft at which it is existing, and it is heeling, that is the draft at which it is heeling. Okay, that is what it depends on. And if the initial draft is here, there will be some value of M0, it will be here. If the draft increases or decreases as it goes up or down, your M0 will be at some other point. So, your Km0, which you call as okay, there is no term for it, Km0 as it is, or your metacentric height Gm0, any of it will depend upon your draft. Okay. So, right now here we have Km0. Suppose you are given Km0, that is your hydrostatic, from the hydrostatic data we have Km0. Once you have that, then using this equation you can get M0 M1, provided you know P. Okay. One way to find P is again from the hydrostatic data, that is what will happen, that is I will explain. That is, what happens is that ship is initially put, I mean, it is in the dry dock, there is some draft, it stays at some draft, then the draft keeps coming down, okay, and finally that due to that change of draft there will be a change in volume, okay, in the displacement, and correspondingly a change in the upthrust, okay. Now that change will be borne, or it will be taken up by this P finally. When it comes down, that difference will be taken up by P, that is the reaction force. So suppose you see that the change in draft, suppose you see that the change in draft is something, okay, that will be given, that if we know, once we know the change in draft, we from the hydrostatic data again we can find the hydrostatic curves, in fact. So that also I explained, that is usually we are given some curves which will say draft versus displacement. So once you are given the, so for each draft you will know what is the displacement of the ship once you know the hydrostatic curve. So that of course you need to do this problem, but once you design a ship you are going to design all that, so that initial design, once you do all the design, all this comes with you, this is known as a hydrostatic curves, the whole thing comes with you. So you look at that, you find the displacement at each draft, so you find the change in displacement. That draft you can always read, I mean any dry dock you can easily see the change in draft, read the change in draft, read from the hydrostatic curve, find the change in displacement, find the change in weight, that is P, that will be borne, that when that touches the ground that will be borne by the weight of the keel block, okay, that will take the weight. So that is what this is. So this is the first way of doing it. So you know Km0, from here you know Km0 M1 means the change in metacenter. So if you do Km0 minus M0 M1, you will get your Km1, okay, that will give you. And if you know the position of G, I mean if you know Kg, then note that in this method of derivation G is not changing, G is fixed, therefore this Km1 minus Kg will give you your Gm1, and in these derivations we usually write it like this, G0, because G is not changing at all, so it becomes G0 M1. So there are, initially there was G0 M0 which was before the vessel touched the ground, before dry docking or before the critical instant. I defined critical instant is the instant at which the ship touches the keel block. So before that it is G0 M0, then it becomes G0 M1 according to this method of solving the problem. So this will give you your new position of Gm, G0 M1 is your new Gm, okay, and if this Gm has become negative, you know that the ship has become unstable, okay. This is first way of doing it. Then the next way of doing the problem is same thing, I will do this. So this is the center line of the ship, initially you have G here and you have the weight W acting. Now what do we assume? We assume that there are two weights. Now we have, of course at this point there is B, the center of buoyancy, and of course there is a W minus P acting here, but that is not, we are not bothered about the buoyancy part in this problem, in this way of definition. So what we are doing here is that we assume that P, which is the reaction force, is like a negative displacement. So right now we have two displacements, one is the weight of the ship acting down, and there is a negative displacement P acting somewhere to the side, okay, or to the here acting here, there is a negative displacement. So what do we have? We have a resultant which is W minus P, actually it will act somewhere, if you do it you will see it will come here, since the forces are in opposite directions it will come here, W minus P will be a force acting here, okay. Now same concept as before, W minus P will be the centroid of these two forces W and P, we can take the distances as this as x, let us take this as x and this as y. Then so see, what you have here is this is your G0. In this particular case, what you have is, so before you have P coming, you just have W acting at G0, this is G0. Once you have this P coming, you are assuming that there is a new displacement which is a resultant of this old initial displacement, this W and the reaction force, which is W minus P. It is acting at a slightly different point, it is acting here, this is G1, okay, G0 and it is G1. Now in this method of derivation, what has happened? Your G has moved up, okay. So actually it makes no difference, you will see when you do, the slight difference is there of course in the calculations, but like 0.1, 0.2 meters you will get a difference, but other than that you will see that when you do the GMs using the two methods, one in which you assume that there is a decrease in the metacentric height because you assume that P is actually a buoyancy force, or number two, you assume that P is a negative displacement. In that case, there is an increase in GM, increase in the point, or a going upwards of G goes upwards, there is a new G. Now that either way, whether G goes up or M comes down, there is a change in GM, there is a decrease in GM, that remains same, and it is just the way in which you look at it. Let's derive this expression. Now same thing, we say that now as you can see, W minus P is the centroid, therefore W into y will be equal to P into x. This is W into y is this distance, is P into x. So P into x is a moment causing like this, W into y is a moment causing like this, they are in balance because this is the centroid, okay, at that point. Then now it is just some like x, you can just look at these figures, you will see you know what is G0, G1. See, you have to make these triangles, this is K, okay, you make this full triangle. So you get, look at this triangle, you will get this kg sin phi, and y becomes G0 G1 sin phi, then therefore W into G0 G1 sin phi equals P into K G1 sin phi, or W into G0 G1 equals P into K G1, W into G0 G1 is equal to P into K G0 plus G0 G1. Therefore W into, or you can, I will just bring the W minus P into G0 G1 equals P into K G0. Therefore G0 G1 is equal to P into K G0 divided by W minus P. Now what did we get for the previous thing? We saw that in the previous case we saw that M0 M1 was P into K M0 divided by W, okay. Now at any rate you need some this, we will see how to we will do some problem to compare the values. So this is two ways in which you are doing the problem, one in which M comes down, one in which G goes up. Problem is the same, it is just two ways of doing the problem. Okay. Then now what I thought this time is that these problems that I am having, instead of my writing down all this, I will put it in the screen. So you just read it like this. For instance, the first problem, I did not write the whole problem. See, the problem says that you are given some ship that is to be dry docked. This I started last class. Now see, you are told that the ship is initially at a draft of 5 meter, okay. Okay, don't show my hand. So it's at a draft of 5 meter, then displacement is at given at 17,052 tons. Now, some oh, that is a good point, I did not think of it. Yeah, okay. So 17,052 tons. Then what happens is that the P keeps increasing. Okay, the ship is being dry docked. So slowly the weight of the or the displacement of the ship, the draft comes down, and therefore the buoyancy decreases and the weight displacement W minus P decreases. Now, or rather in this case you can see that the P keeps increasing. I have not written down the values. Now, this is the problem is that you are given the hydrostatic data, you are given Km, this without this you cannot do. Okay, Km values are given, like different values at different drafts have to be given. I did not write the whole value, but that whole there is a big table. So, like this 14.08, 15.06, like this the Km 0 will come for different drafts. And now your question is, find out the draft at which the ship becomes unstable. Now, how will you figure out the ship is unstable? You will figure out by saying that at that point GM becomes negative. Okay, yeah, GM becomes 0, exactly. So, GM becomes 0. I mean, when you are doing this table, at some point you will see that the value becomes negative. Actually, you have to find it at 0, exactly. So, GM becomes 0. So, you have to do that. Then so for that you need to find out how the GM keeps decreasing. Now, this is a very straightforward problem. We have seen how the GM keeps decreasing. There are two ways in which you can solve the problem, as we said last time. You can keep decreasing your M and find your new values of GM, or you can keep increasing your G, raising up your G and finding out the new values of GM. In this particular problem, they have actually trying to I do not think there is anything like that. If you do that, there is a slight difference. First of all, actually you should get exactly same. It is because of errors in the values of, see, Km, it is not always accurate, means like here you see this draft Km 0, 14.08, 15.26 like this, they are not absolutely accurate. There is one problem which does both values and sees which is, I mean, how close they are. The differences of the order, we will do it and see, the differences of the order of I mean, I will give you 0.5273 meter GM, and the other case GM becomes 0.5239, 5237 and 5239, something like that. So, the very difference, it's both are same, but actually we are doing the same thing, because if you think of it, actually you can see P in the derivation, P is really not a buoyancy force, or it is not a negative displacement, but it is something that can be seen as both. There is nothing wrong if you say that P is a buoyancy force, because it is like a buoyancy force, it is acting somewhere up in the upward direction, it behaves exactly like a buoyancy force. So, if you do the and you know that initially the ship, there is some at that point there is some buoyancy force, and when it is coming down, means when the buoyancy force shifts, wherever that buoyancy force is acting, wherever it is hitting that center line, that is the meta center. So, it is the final meta center. So, that is absolutely, there is no assumption in any of it, approximation, there is no approximation in either of these derivations. So, both are absolutely correct. So, no such thing as which is better or anything, but usually they use this one Kg better, because the other one you need Km0, because hydrostatic data Kg is known always, because it is the very important thing. Km is not that commonly used. So, because of that, I would say that we will use this one Kg instead of Km. So, this formula is more useful than the other formula, though both are same. Then, okay, so in this case what do we have? We have displacement is given. As you can see, this column displacement at 5 meter draft 17,052, this will remain the same, okay, all throughout, because it is at 5 meter draft. Then there is no point in this column as such, but then this is P will keep increasing, 0 it becomes 1,800, 2,000, 3,000, 5,000 like that, P keeps increasing, and therefore, W minus P will keep decreasing. So, the value 17,000, it will keep decreasing, it goes down up to, in fact up to 6,000 at around 2.5 meter water line, it will be, by that time it will become about 8,000. Okay. Now, the only thing here is to do this thing, this formula. Okay, this of course has to be given, kg0 has to be given, it's the center of gravity of the whole ship, that has to be given. kg0 means when the ship is designed or when it is not, it's not about dry docking, when the ship is in its usual condition, what is its g0, that we need to have. It is given in this problem is as 11 meter, and kg1 is your new kg, which keeps varying as the draft keeps changing. So, as the draft keeps going down, g keeps going up, okay, and as a result your kg1, which is equal to kg0, no sorry, g keeps going up, exactly. So, kg0 plus g0 g1, okay. So, your g1 keeps going up or g keeps going up, and therefore, your kg1 keeps becoming kg0 plus g0 g1, and at any point g0 g1 is given by this formula, P into kg0 by W minus P. Everything we know, that is the only, P is, again I told you, P is the displacement at every draft. So, this needs the hydrostatic curve again. You look at the hydrostatic curve, you have the draft. For the draft, you read the displacement from that curve, from the hydrostatic curve you can read it directly. So, when the draft keeps decreasing, your displacement will keep changing, or total displacement will keep coming down, it becomes W minus P, and therefore, you from that you get this W minus P at each. The thing is, you keep doing it at steps, like draft you change from 5, 4.5, 4, 3.5, like that you keep changing it in steps. As a result, the other one will also keep changing in steps, and you put it in this table like this, and so you keep doing this. Now, see this km0, please note km0 is also not a, it might seem as if the km0 is a constant for a whole column. I should have probably written a couple of more values, but this km0 is not a constant for the whole table, because km is defined as a value. That is another thing, kg for instance does not depend upon the draft in that sense, okay, because it is the weight of the ship, g is at the, that does not change, but those are some of the advantages of the second method compared to the, but km will change, okay, it depending on the draft m will be at some point, okay, and when you change the draft m will shift, it will come down or go up. We can actually think, actually here I will draw this figure, it looks like this. So, km0 or all these values km0, it actually comes down like this.
So, this should be km, so not km0.
No, it is km0, that is good, that is a good point, but it is km0 because m0 means when the ship is in an upright condition. Ship can be in an upright condition at different drafts. It is at different drafts, but in the upright condition. That is the meaning of 0. Okay, there are two processes happening here. One is healing. That is what metacenter is really associated with. Okay, and the other one is the change of draft. Change of draft, I mean, all that you did previously was just dealing with healing. There was no draft, was all fixed. We never talked about draft at all at that point. I mean, there was a draft, but no change. This time m0 means 0 healing, that is all. Here the draft is changing. So, that is what. So, km0 comes down like this. So, this is how your km0 will vary. So, as your draft keeps increasing, your km0 is actually coming down. Okay. Then, okay, so this kind of explains how the km0 comes, and that is how this table also says km0 will actually change. So, correspondingly here what is happening, the draft is decreasing, therefore, km0 should increase. Yeah. So, km0 will keep increasing 14.08, at the end it becomes 28.8. So, km0 will keep increasing. So, this is your problem, I mean this is quite straightforward. This is the process of dry docking. This is how you calculate the. Now, the others are just problems which just with some twist and all that, that we can do, we will do. Now, one more thing is that I have already told you a ship is mostly trimmed by the stern. Now, we are going to kind of combine the two. We have already done trimming. Now, we are going to combine trimming with dry docking, okay, or when you are dry docking, if you remember in trimming we talked about a change in density and that produces a change in draft. As if you remember, that produced a trim. Just like that, this is also a change in draft due to a different reason. This also produces a trim. Okay. Now, we will just do at the instant of dry docking. As I told you before, in dry dock, I mean in general, ships move like this, means the stern is down, the bow is up. Okay, always in general, the ship is always like this, and when it is dry docking also it is like this. So, it comes down like this. So, in general, in 95% of the cases, this will hit the ground first. Okay. So, this is where the ship first hits the keel block. Now, when that happens, let's at that instant, the critical instant which we call. So, when it keeps coming down, it will hit. So, at that point there is a P acting here. Okay. It will be acting only at that point. It is only this point as hit. We, for the simplicity purposes, for our purpose, we will assume it is the aft perpendicular. So, the aft perpendicular hits the ground first, and at that point the P acts up, and therefore, what will, because of this there is some trim going to happen. We always defined change of trim is equal to the moment causing trim divided by MCTC. That formula you just memorize. That is, it's very straightforward, and it's so this one, change of trim is equal to moment causing trim divided by MCTC. So, the new moment that comes here, I mean the new force that comes here is actually this P. Okay. So, this P will give the new moment. So, what will be, remember, moment is always taken from the center of flotation, that is how we have defined it. Therefore, the new force that has come is P at a distance of, we usually define the distance of the center of flotation as small l. If you remember the derivations in the previous chapter, small l represents the distance between the aft perpendicular and the center of flotation. So, the distance between P and the center of flotation is small l. Therefore, a moment causing trim in this case becomes P into L. Okay. So, the change of trim becomes P into L divided by MCTC. This is a particular case, and for the purpose of this course, you can assume that if you have a problem where you have dry docking combined with trimming, always you will have the aft perpendicular hitting, and this thing holds, this formula holds, and you have the change of trim given by this formula. Change of trim is given by this formula, P into L by MCTC. Okay. Now, so we write, this is usually written as T, I think T is equal to A, or just T into MCTC by L. Okay. Okay. Now, we have some problems. I put the problems up in the screen now. I will put it here. You can read this. Okay. Now, this is the problem. So, a vessel is now about to dry dock, and it is said to be in the following condition. You are given that the draft forward is equal to 6.1 meter, draft aft is 6.7 meter. Oh, and this is a particular case, draft forward is more than draft aft. Then Km0 is 7.2, Kg0 is 6. These have to be given. These are the hydrostatic data. Then MCTC is given, TPC is given. longitudinal center of flotation is 80 meter forward of aft perpendicular, length is 180 meter and displacement is 11,000 tons. So, you are told that there is a critical instant when the ship hits the oh actually 1 minute, something I no, it's correct only, sorry. That is draft forward is 6.1 and draft aft is 6.7. So, aft is more, I do not know why I got anyway. So, all right. So, length is 180 meters, displacement is 11,000 tons. You are asked to calculate your GM at the critical instant. So, the question is, the moment you are asked to find GM, you know what you have to find. You need to find that G0 G1 definitely, that means you have to find the change in G. Okay. The initial GM you can easily see from the look at the data, I mean look at the problem itself, you are given your initial Km0, you have your Kg0, you can find your G0 M0. So, that is directly given. You have to find your final GM which is written as G1 M0. Okay. This, see, we are not changing M here, M0 we are not changing here, we are changing G1 M0. Okay. Therefore, our problem is to find G1 G0 G1. Now, okay, now you need to find your G0 G1. G0 G1 is always given by this formula P into Kg0 by W minus P. Now, as you can see, we need to find in this problem Kg0 is known, we need to know P. So, we do not know P. Now, how can we find P? It's, as you can see looking at the problem, aft is below, therefore, it is going to dry dock like this. At the critical instant when it touches here, P will come here acting here. So, P into L by MCTC will give you your trim. Okay. Now, what we can do is that, no, it is not an assumption, see the ship will go like this only. So, you know what is going to be the trim, you are given the trim, the initial trim is given, aft is 6.7 and forward is 6.1. So, the difference is the trim, you know the trim, and therefore, you can find P like using this formula, P equals T into MCTC divided by L.
So, here T should be changed in trim.
Yes, sir, and it is the trim.
T is the initial trim.
In this one, it should be change in
Change
trim.
of trim.
Okay. What they have assumed here is that, see, the ship trims like this, okay, it comes and hits here and then the trim becomes 0. Okay. It comes like this, it hits here and then it becomes, so the change of trim is the current trim. Okay. That is the problem, how the problem is done. I mean, that is how you do this kind of problems when it is so when it initially comes like this, hits here and then sits down. So, the change of trim is equal to the trim is equal to T into MCTC by L. So, this gives you P. Okay. This is the critical instant when P this touches here and then it just sits, and therefore, at that point T into MCTC by L will give you P, that you can just do, in fact it will give you. So, you are given your trim is 0.6 meters. So, 60 into 155 divided by 80 becomes 116.3 tons. Okay, in this problem, so now you can then once you know P, okay, you can do this, you can get this G0 G1. Now, they have also done it using the other method where you do M0 M1 instead of, this is why this is to just compare it, the formula is this P into Km0 by W, Km0 is given. So, P is known and therefore, and W is also known. So, this will give you your M0 M1. Now, the two ways in which you can solve is, now you you have your G0 M0, you have your G0 G1. So, you can find your new G1 new GM, which is your G1 M0. From this you find this is your problem. Now, other thing is, you know your G0 M0, then you know your M0 M1, then you sum them up to get your G0 M1. So, these are two ways in which you will have G0 M0 initially, then you will have G0 M1 or G1 M0, either of these two. So, actually there is a slight difference between the two, and the other one is, so these two, this much difference is there between the two, 0.527 and 0.524. So, yeah, that becomes, it's very small, it's negligible almost, because that much of error will be there in your hydrostatic data anyway, you won't get that accurate anyway. So, it's just a, now in this problem you can see you are asked, the second question is writing moment at 1 degree heel. Okay. Now, it has touched, and at that point let us assume that it has a 1 degree heel. At that point, what is your writing, how will you find the writing moment anyway? Writing moment has only one formula, you do it using Gz, you need to know Gz, that is all. So, Gz is and you just need to know the formula. Okay, we need to put it as G1 M0 sin phi, that is all. GM sin phi, you just need to know which GM it is. This will give you your writing moment, writing arm. Okay, from that you get the writing moment. So, this you need to find out. Again, in the, if you do the two methods, there is a slight difference. I mean, two methods means when you use your two G1Ms, like 100.2 and 100.5, there is a slight difference in the answer, that does not matter, that is okay. Then how will you find out your the moment it touches, when P comes, what will be your bodily change in the weight, bodily change in the displacement at F? Means at that, we call it parallel rise or parallel sinkage. It will actually be rise in this case, because P is coming upwards. Now, what has happened? There is a force P acting upwards at this instant, there is a force P acting upwards, and when a force P is acting upwards, what will be? It will be just P by TPC, that will be the change in the parallel sinkage. P is a force acting and TPC is given. So, parallel rise or sinkage will be given by P by TPC. Okay. This will give you your bodily rise or sinkage, and okay, that is all. Okay, then I think we can do the next problem. Okay. All right, then this problem states that, yeah.
Sir, in this problem, sir, we have used critical point as the ship has completely sit on the dry dock.
It's a small difference, yeah. It is at the point where the aft touches the keel block.
Yes, sir, but it is a critical point. But here we have used that critical point is that when ship has completely is on dry docking.
Where have we used?
Ship is completely dry docked. So we have used this
Because
as critical
changing
point.
trim
Here.
we have
Yes,
taken
sir.
as protectory.
Um,
The force PB found out at the instant when ship sits on the
Ship
keel
completely
block.
sits on the keel blocks.
there is one slight assumption like that, yeah. Let me see here. Okay, I will check why that is done. I have to read this section. I will tell you in the next class why. Okay. Then this problem says that a vessel is about to dry dock in the following condition. You are given the draft forward and draft aft, then Km0 is given, Kg0 is given, MCTC is given, LCF is given 62 meters forward, length is 118 meters, displacement is given. Okay. Now, you are told that at the critical instant your GM should be 0.45 meter. Yeah, in order for that to happen, how much ballast should you transfer from a double bottom tank with a kg of 0.5 meter, 30 meter forward of AP to a double bottom tank with a kg of 0.5 meter, 90 meter forward of AP to ensure that the vessel is in a satisfactory condition. Problems are more or less similar. I mean, the question is more or less similar. Always what you need to find is mostly the yeah, actually in all the problems they have taken, I will say that. Okay, then the problem becomes so you are in this case, so you are given your initial trim, you have the draft and forward and aft, then do you have P here? Okay. Let us see, G0 M0 minus G0, do you have your M1 here? M1 Kg0, okay. Actually, this problem is slightly more simple. In fact, see, you have your Km0 and Kg0, that means G0 M0 you know. Now, you are told that your GM should not be less than 0.45 meter, that means you can assume your final GM to be 0.45 meter, that is how you do it. So, that means you know your G0 M0 and you know your G1 M0, therefore, you can find G0 G1 directly, and actually using that formula you can go backwards to find P. Okay, you know G0 G1, so you go backwards to find P, and once you know P, you can find how much trim will happen when it touches at critical instant, and so you know your final trim, you know your initial trim. What is the question is to find the ballast to be transferred. Okay, then now you know your final trim and you know your initial trim, so you know your change of trim, and you know that change of trim is equal to moment changing trim divided by MCTC. So, you know you find the moment changing trim, and the moment changing trim is W into distance moved, that is all. W is the weight that is given here. No, that is a question here. W is the question and you are asked to find D. No, D is given and you have to find W. The problem just goes like that. So, I will just quickly write the steps. So, you do M0 M1, which can be found, okay, you can do it using this form. Anyway, it will be G0 M0 minus G0 M1. You can write it either like this or using G0 G1, it is the same thing, is equal to your initial G0 is given 0.5. This you get using, actually all these formulas if you know, then these problems can be done. Km0 minus Kg this thing minus G0 M1 is given as 0.45. So, this can be done quickly. Then we use the formula M0 M1 is equal to P into Km0 divided by W, that is also. Now, here we know M0 M1 W Km0. So, you find out P. So, we know P now. Now, we are finding that the final trim if let us assume it is T, then P into T is equal to P into L by MCTC. Now, from this you know P is known, L is known, you know the final trim, you can find the final trim. Okay, this is calculated. Now, you know your initial trim, I mean these things it should be clear. Initial trim is equal to forward draft, I mean it will be aft draft minus forward draft. This will give you your initial trim. Both of these are given, initial draft in the aft and in the forward are given. So, aft draft minus forward draft will give you your initial trim, which is the present trim. The final trim, if the GM is satisfied, is given to be this. Okay. We do not know aft or forward, but we know the total. And how will you find aft or forward if you want to find? There was another formula, means you have the total trim. How do you find the aft and forward drafts?
So changing the draft forward.
That is what we had a formula like this.
L by L into.
Yes, change of trim forward, I think this is aft. Aft is equal to L by L into total T. This formula was there. So, if you use this, change of trim aft is this, and change of trim forward is L, capital L minus small l by capital L into T. That will give you your change of trim forward, and then you can find that forward and aft trim. Then okay, now once you have this, you use the formula change of trim is equal to moment changing trim divided by MCTC. Therefore, you know this, so you can calculate the moment changing trim. Okay. Now, once you have that moment changing trim is equal to W into D. So, D is the distance through which the ballast has to be transferred. That is given, as in this particular problem it is transferred from, see when you are given this problem, like it says, okay, this is an extra information, kg of the tank. I do not think we need that, kg of the tank is not needed. So, you are told that this is not needed, this is additional. So, you need this 30 meter forward of AP to 90 meter forward of AP. So, the distance through which it is moved is 60 meters, forward of AP it is moved 60 meters, and therefore 60 into, therefore that is all. So, D is 60 meters. So, W into D will give you, so this will give you your answer. Okay. Okay. So, I think I will stop here. Okay. All right. Thank you.